All right, welcome back. Today is November the 16th, and this is our last week of classes. So it feels like yesterday, right, when we started, and now, boom, it's gone. All right. So everything in life has a beginning and an end. All right. So we're going to continue here, have letter H to do. So this reaction, what do you think it is? You have an organic acid. Uh, TSOH is an acid. Is toluene sulfonic acid. It's not a. You're not making a good living group there. So it's plain acid. So this is an acid. So the oxygen from the alcohol grabs it, and those electrons are transferred to the oxygen there. And so you're gonna make water, and that's a good living group. You'll count your carbons 1, 2, 3, 4, 5, 6. You'll form a carbocation here, and that's your first intermediate. And then the tosylate. Now do you think this is a base, but it's not a nucleophile because it's just not a good nucleophile, and that's because of the sulfur groups are making that oxygen weaken, so it would not go and attack. So your chances are you can deprotonate here or here. All right, so how many products can you make from those two combinations? 3. Very good. So first is the Huffman. So here will be your Huffman. And then you have 2 side shifts. One is trans, and the other one needs to be cis. So 1, 2, 3, 4, 5, 6. So this is your cis. Both of these are side shift, and the trans will be the major. All right. All right. So let's do the next problem. PBr3. So, what was it? What type of reaction is this? This will be an E1, right? Yes. Because let's see, is it E1? Yeah, it's E1 because it went through carbocations. All right. All right. So on the next one, this is a pure SN2 reaction, where the OH will be transforming to bromine. So the only thing you have to think about here is this bromine going to be up or down? Down. So this is a pure SN2 with inversion of configuration. All right, next is a ring opening of an epoxide under acidic conditions. So this is acidic conditions. This is a pure SN2 borderline, right? All right. So the reaction mechanism here is that this oxygen grabs this H. Those electrons are transferred to the oxygen. Then you make the intermediate that you make will have an elongated O bond here, that this one is plus, and have one lone pair. This methyl group is towards us. This H is towards the back, and so this carbon is partially plus. All right. So the nucleophile that you have here is methanol, and that's going to attack where? Must substitute it. So it's going to come right there, hits it, and those two electrons that are on this bond will be transferred to the oxygen that has the plus. All right. That will make the following molecule. So do the anti-periplanar product first. So you have the OH like that. This will be your methoxy. We'll lose the H from another. We'll lose the H from perhaps the conjugate base of the sulfuric acid. It has to deprotonate, right, to form that. And then this methyl will be up, and the H will be towards the back. And it was flipped up a little bit. All right. That's nice. All right, let's do the next one. What do you think you have here? SN1, SN2. It cannot be E1 or E2. SN2, very good. All right, primary, exactly right. So because it's primary, it cancels the SN1. So it's totally SN2. So check this reaction mechanism will be the oxygen grabs the H. It transfers the electrons from the H Br bond to the Br. And now you have this. And then here you have H, H2O plus with one lone pair. And bromine is back with a vengeance. Right? So it comes around here. And 1, 2, 3, 4, 5, 6, 7, 8 attacks. Oh, that was a weak kick. Like that, more direct. Boom. Kicks it out. Kicks the water out. Now you have a bromine here. And water that was kicked out. All right. So this was an SN2 reaction because the leaving group came up from a primary alcohol. All right. So the next one is simply protection of an alcohol. This is not an SN1, SN2, or E1 or E2. Simply just kicks the chlorine. And count your carbons. You have 2, 4, 5. And you protect your oxygen with a tosyl group. All right. All right, let's do the next slide. This is gonna take a little more time, so we're gonna spend most of our time here. All right. Okay, so I want you to help me out with this one. Okay. All right. So next semester will be easier in a way because you'll be able to use all your creativity and do these problems, on a paper. This semester have been rough because I had to draw everything and give you options for multiple choices, and we really haven't really grasped the utility of the multi-step synthesis. But nonetheless, I still have to teach it to you. So whenever you have a problem like this, you have to look at what you start with and what you're ending with and see what's new. All right? So I noticed that this portion of the molecule hasn't changed here. What is new is this thiol group. That is what is new for me. All right? And please pay attention, whether you take OCHEM with me or not next semester, you will be asked this kind of problem. So it'll be interesting how you can react and see what you get. So we're going from an OH that is up to an SH that is down. What is the first thing you think about when you see that? SN2 reaction, exactly. So we have to now simply convert now the OH into a good leaving group. What would be the option for it? If you add an acid, you make, you could do an SN1 reaction. That is the problem. So, and it will rearrange, and it will end up substituting right there. See what I'm saying? So think of another way of making the OH into a good leaving group. A what? That's the same thing that he suggested. Yeah, adding the acid will make it water. That will turn it into an SN1 reaction. You need an SN2 conditions. For this particular problem, there's only one intermediate, which is good. What about a tosyl group? Right? So turn the OH into a good leaving group. So put a tosyl group there, and there you are, ready to do the forward steps now. Let's go forward. From here to here, what do you need? Tosyl chloride and pyridine. And that makes that. And from here to here, what will you add? NaSH, And I need a polar protic acetone. Yes, that's good. I had DMSO, but I'll give you that. That's good. So so that's why it says, see me if you find out if your answer is acceptable. I usually have that for my students because there's several ways of making this. Matter of fact, I met a guy in college. He was kind of my friend, not really my friend. He was more like my nemesis in karate. Actually, I beat him 4 times. My record against him was 4-0. But anyway, he was kind of weird. And I met him in Florida, and he was from Hong Kong. And I never forget that he said to me, because he was also a chemist, that there are too many ways to skin a cat. That's why he said, when it comes to reactions, he always thought that's what he used to say. And it stayed with me forever, that phrase. So there's too many ways to skin a cat, because he's from that area where they eat cats, I guess. Poor kitties. So here we need, this will be an SN2 and a protic solvent. All right. So the next thing, notice that my level of difficulty, this is me having fun. This was a private and corporal, sergeant, lieutenant, captain. I have made it all the way to general sometimes when it gets really, really crazy with RNS. Bigger molecules gets really difficult. But nonetheless, students are still capable. All right, so check out the next reaction. This is what you need to do. You need to do your, basically what I call it sometimes, this is my chemical inventory. So I notice that I have a benzene ring and 2 carbons, 1 and 2 here in the triple bond. So that means this carbon and this carbon right here will be part of that. And I don't have the carbonyl included. So this is what's new. That's new. The carbonyl is new. And this 1, 2, we're adding 2 carbons to this molecule. All right. So if you have a triple bond and you see a carbonyl, what is the first thing that comes to your mind? That it came from an enol, right? Came from an enol, and it did tautomerization. So a lot of my students, they have told me that sometimes they cannot think the problem backwards all the way. So it's always a good idea to sometimes to meet in the middle. That's fine too. That's a good strategy. Actually, that's a strategy that I think I used when I was undergrad. And so think of way of going forward and backwards and get in this in the middle if you get stuck. But I won't get stuck because I made this problem. No, just kidding. That's the only reason I wouldn't get stuck. No, I'm serious. There's only one common intermediate here, and that is the benzene with the triple bond and an ethyl group there. There you have your, let's see, 6, 7, 8, 9, 10 carbons total that you need. All right? All right, so we can solve this. Going from here to here, what would you do? What would you add? Mm-hmm. Yeah, and something like that, right? So that would be exactly what I would do, or use ethyl bromide instead. That will give you there. And how will you go from here to here? And what's the name of that reaction? You remember? Hydration, exactly right, with tautomerization. Very good. So here you will add water, sulfuric acid, and mercury sulfate, which does absolutely nothing in my opinion. And then you get, this is called hydration with tautomerization. All right, that will give you the final product. Notice that the OH will attach here on this carbon, and the H will attach here. Because why? Why is that? Why the OH will go to that carbon in particular? What kind of carbon is that? Benzylic carbon. So it's more reactive. It'll leave. It will, and also hydration will. Let's see. Yeah, that will be preferred. That will be the preferred carbon to have the OH because it's benzylic. Mm-hmm. All right. All right. Let's do the next example. Let's check what is new and what stays. So right now, my carbon chain looks like that. All right. So what is new is the OH. But notice that the OH is on one carbon down from the double bond. Another thing you're going to notice that usually the intermediates for this type of reactions are either alkenes or alkynes. All right. Okay. So, all right. Check this out. This is a problem that I would start from the right. Because if I see an alcohol there, I know that I can make that alcohol coming from an alkene, right? So 7-member ring. So I will have that form. That will be my precursor for that final step. And thinking forward now, what kind of reaction will you add there? Let's solve it. How would you go from here to here, if that's the case? Yes, so hydroboration, right? So first, BH3THF. Second step will be hydrogen peroxide in the presence of sodium hydroxide. All right. And this is hydroboration. All right. So, going backwards, I envision that I can have the OH be the product of the starting material. Look at this. What if I have this now? How cool is that? So the intermediate between an alcohol product is always an alkene. You notice that? So if to go from here to here, that's easy. Oh, by the way, notice that this double-headed, no, this arrow is not double-headed. This arrow has two lines, and this is a retrosynthetic arrow, and it always points towards the starting material. All right, that's how you get it right. All right, let's solve this going forward from here to here. What would I use? What's the name of that reaction? Lucas, you know it?
I guess you could do oxymercuration.
You could do oxymercuration, yes. Hydration, that's the one I have. That's easier. Cheaper materials, just water and sulfuric acid. Yep, exactly right. And if you ever run a lab, you will see that you always want the cheapest material possible. All right. So yeah, so this will be hydration. Very good. Because they will be more dumb. They'll be dumber. Yeah. Well, if they have a truckload of money for research, yeah, they can do it. They can do the oxymercuration for sure. Yeah. Some people are crazy and they will go and do it. Other ones they simply don't know. And then, oh, this is the first reaction I know, and then they do the most expensive one. All right. Yeah. All right. How about the next reaction, going from the middle to here? What would that, how can you do that? I have three ways here. I have three options. I'm gonna write the first option. Remember this is an option that we've been trying. POCl3 in pyridine. All right, that makes an elimination. This is an E2, by the way. We're thinking, wait, yeah, this will be an this will be an E2 reaction. How about you think of two that are E1s? Dehydration of alcohols, remember that? So if you have concentrated phosphoric acid or concentrated sulfuric acid, those would be E1s. You get elimination also. You get an alkene. And there you have it. You beat the sergeant. All right. All right, let's do the lieutenant now. Okay. First, check what's new from your starting material. So this is my starting material. This is my final product. And so this group is new. All right. Now, notice that any time that you see an oxygen attached to another carbon that has an oxygen on it, that the precursor for those two oxygens was an epoxide. All right. So going backward, if I know that premise, notice that I can just say, okay, I'm going to take this and convert that into the diol. How would I do that going forward? Let's solve that step so you can get it into your long-term memory. What would you add to that? Make it acidic conditions SN2 borderline. How would you add it? What would you do? Yeah, you're close. You're close. How about just give me the cheapest material in your lab right now? How about water with a drop of acid? H3O plus. So you say HCl, so that's good. No, you say H2S. You said sulfuric acid, right? So yeah, you were really, really close. All I do is H3O plus. That will protonate the epoxide, and the water from the H3O plus will go and attack and do the nucleophile. The water will put this group, and more water will deprotonate that H, to make it neutral into the OH. It makes sense? So that's how you will make that. Excellent. All right. Let's say we're going backwards again. What would be the precursor for that? How can you make an epoxide, right? Well, there's several ways. Sodium hydride. Yep, you can do, sodium hydride, exactly right. Coming from what? So remember, we still have to keep this. That's exactly right. So going from here to here, you're suggesting a cyclization with sodium hydride. And so notice that I need to keep the OH, because I start with it from the beginning. So I keep it. What do I need to put here? What do I need to put here? A leaving group. What's a good leaving group? Iodine. I like bromine. Bromine is more versatile. I'm going to show you why. It's in the middle of the halogens, and for example, we can do the halohydrin reaction going backwards, but I cannot do it with iodine, and that's the only reason. I would choose bromine, and then this was the precursor for that halohydrin reaction. So this is the halohydrin. Hold on, not that. This is the precursor for that. From here to here is the halohydrin. 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 And so, what do you need? Bromine and water. All right. And what would you do from here to here? Similar to what we have here, right? So POCl3 in pyridine, or concentrated phosphoric acid, or concentrated sulfuric acid. All right. Okay, the captain seems a little bit more challenging here, but we can do it. Yes, sir.
So if we just do the elimination and then use like osmium tetroxide, could we get the same product?
Oh, that's a really good idea. The answer would be yes if I give you that both of these are wedge. But if I give you one up and one down, you have to go this route. But I didn't specify it. If I didn't specify it, by all means, just you go from what and this has happened in my milestones. Someone will come up with this. Actually, you can probably go also from here to here with an epoxidation. You see that? That will be MCPVA. See, we're skinning the cat differently. And this one will be osmium tetroxide. And then that's the first one. And then we need something like sodium sulfite, something like that. That will give us final product. Very good. Yeah, excellent. All right, how about the next problem? Okay, so this is a little more elaborate. Notice that here we have this portion of the molecule did not change. All right, what's new? Where the bromine was, I have now a carbonyl group. So this is new. And also, this is this one, CH3 oxygen. That's a methoxy group. But the software usually types the H's backwards, which is fine. I like it too. So this is a methoxide group. Those two are the new things that we have. All right. All right. So let's dissect this. So now notice that from my bromine, it's not bad. So I know that from my bromine, I envision an alcohol. I switch it from it came from an alcohol, and then from the alcohol I oxidized it and then made the carbonyl, right? So my last step will have my previous to last step will have an OH group there instead of the carbonyl group. So with confidence, I'm going to draw it. So I'll have this one will be that. This is what I'm telling you. That is that. And here I have a methyl group that is down. This group is always up. And this is going to be important. That group is bulky. So if I want to do anything on that other side of the molecule, it's going to be pushed down. So most likely, this oxygen will be forced to be down. All right? And if you don't see it at this point, simply put a normal line there, a regular bond, and then you can trace it back. Because from here to here, it's simple an oxidation of an alcohol. So what will you do? What would you use there to oxidize an alcohol? What would you use? Give me an oxidant. Jones reagents will work here, yes. Give me a milder one. PCC, exactly right. I love PCC. It oxidizes and it goes into the aqueous layer when you're working it up. It's really nice. It does its thing and leave. It's not a seagull chemical. You know what seagull chemical is? Ones that goes to the reaction, flap its wings a lot, leaves everything crap, and then it goes out. then you have to clean up that reaction. That is a seagull chemical. We don't want that. But yeah, PCC is pretty clean. I love it. So there you go. So next one. So do you see this pattern? Whenever you see an oxygen adjacent to another oxygen, that came from an epoxide. One of them came from an epoxide. Which one came from the epoxide? The OH. Because you either protonate, you did it under acidic conditions, SN2 waterline, or you did it via basic conditions as SN2, and then you protonated on the second step. You see that? So look for those patterns. That was equivalent, and I kind of repeated it like right here. Whenever you see this oxygen adjacent to another oxygen, that usually comes from an epoxide. All right, so we got this. So this reaction came from an epoxide. And now take a look. If, let's say, you didn't know this oxygen was down here and you had like a single bond right there and you weren't unsure, this is when you say, oh, okay, this has to be down, because you have this methyl will be up, and the OH, the epoxide has to come from underneath this huge group that is here, opposite to it. This group right here, the isopropyl, transfers chirality. All right, and so notice that the methyl has to be up. So when the nucleophile comes, it comes in the opposite direction. So it'll be, so you add methanol, and you have to do it under, as you're forced to do it under acidic conditions here. Notice that you want to add the nucleophile in the most substituted carbon, which is the carbon that has the methyl group. All right. Sulfuric acid. This will be an SN2 borderline reaction under acidic conditions. All right. And so, yeah, this methyl is going to hit right here, and it's going to flip the configuration of the methyl, and it's going to open up the ring on the epoxide. All right, so we're almost there. So from here to here, I envision an alkene, right? An alkene is the precursor molecule for a NCPVA epoxidation. Notice that we lose the chirality there, but it's okay. We gain it back here because that isopropyl group has chirality. And what would you do from here to here? MCPBA. This is an epoxidation. Epoxidation. And finally, from here to here, what would you use? Yep. So sodium etoxide in ethanol. Very good. And heat. So sodium also in ethanol, heat, and this will be an E2 reaction, where this guy here will be your Sysef. See that? Yeah, let me write it down. Sysef. All right. We have 9 minutes to do the last page, unless there's a quick question. We're going to finish this chapter today. All right, oxidations and reductions. Let's do the oxidation first. Why do they call them oxidation? Well, you either gain oxygens, that's why it's called oxidation, or you lose electrons. Loses electrons is an oxidation. So loses electrons, gets oxidized, gains electrons, gets reduced, right? All right. So for reductions, you gain electrons or you gain hydrogens. In organic chemistry, that's how you got to see it. All right. Here, let's write that down. You gain electrons or you gain hydrogens for oxidations. You lose electrons or you gain oxygens. All right. All right, so check this out. Here you have a primary, a secondary, and a tertiary alcohol. If you subject them, all three of them, to Jones reagents, which one of them or all of them will all of them we oxidize, and why not? All right, so does Jones Jones reagents, I'm sorry, does it oxidate primary alcohols? Yes, it will. So the question is, where does it oxidize it to? The first oxidation to the aldehyde or the second oxidation to carboxylic acid? Do you remember? To carboxylic acid. It will not stop at the aldehyde. PCC would, all right, but not Jones. So here, the secondary also will be oxidized, and the tertiary alcohol gets untouched because it doesn't fulfill the requirements for oxidation.
It does both of them in the same step?
Both of them in the same step. Yes, sir. Notice that it'll require one hydrogen there for the tertiary. That's pentavalent, but you need a hydrogen on the oxygen, a hydrogen on the carbon holding the oxygen. Therefore, you cannot do that for the tertiary alcohol. So it's stuck. So Jones reagent. Let me write this down. Hydrogen dichromate can oxidize primaries and secondaries alcohols, but not tertiary. All right, let's do the next one. Got 5 minutes. Potassium permanganate. I have a primary alcohol here and a secondary right here. What will I get? So count your carbons. You have 1, 2, 3, 4, 5 carbons. 2, 3, 4, 5 carbons. The secondary gets converted into a ketone, just like this one was converted into a ketone. And the primary gets converted all the way to carboxylic acid. So potassium permanganate can oxidize primary alcohols to carboxylic acids and secondary alcohols to ketones. All right. Okay, so the next 3 problems, I got like 4 minutes. Yeah, I had enough time to finish this. Required reduction. So lithium aluminum hydride. Lithium aluminum hydride, I tell you what it would do. It will reduce carboxylic acids, it will reduce ketones, and it will reduce aldehydes. So right here, this is an aldehyde, this is a ketone, this is a carboxylic acid. So we have all those three, but the double bond, it will not touch it. It cannot do it. So we have 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons. 2, 3, 4, 5, 6, 7, 8. This one over here, the aldehyde will be converted into a primary alcohol, the ketone into a secondary alcohol, and the carboxylic acid into a primary alcohol, and the double bond will stay intact. So right here I can say that lithium aluminum hydride can reduce aldehydes, ketones, and carboxylic acids but cannot reduce double bonds. Okay, let's do the next one. Sodium borohydride. Sodium borohydride is a little weaker than lithium aluminum hydride. So sodium borohydride, I'm going to write it down here. I'll tell you what it does. Can reduce aldehydes, ketones, anhydrides. We haven't seen much of that. And acyl chlorides. Remember this for next semester though. But does not reduce carboxylic acids or double bonds. All right, so what do we get here? We will get, so we have 8 carbons again. 1, 2, 3, 5, 6, 7, 8. I'll reduce the aldehyde. I will reduce the ketone. I will not reduce the double bond and or the carboxylic acid. That will stay untouched. Finally, we have the reduction of with hydrogen and platinum. This is hydrogenation. So hydrogen and platinum, also palladium and nickel fall into this category, can reduce aldehydes, ketones, and alkenes, double bonds, but does not reduce carboxylic acids. All right, so we have 8 carbons again. 2, 3, 4, 5, 6, 7, 8. And so the aldehyde gets reduced to alcohol. The double bond gets reduced. The ketone gets reduced. But the carboxylic acid does not get reduced. All right, and that's it. This is the end of chapter 10. Thank you. Let me turn off the recording.